So, as the title suggests, we are going to consider a very simplistic solution to the Maxwell's equation. It forms sort of the bedrock for any other solution that you may want to conceive. Right? So, these are called the uniform plane waves. We will see why they are called plane waves. Right? The fact that they are waves should not be a surprise. Right? So, let us see what is it about the voltage and current waves that we studied on transmission lines that can be ported over to the study of fields, right, in a homogeneous isotropic media, right. So, the simplified scenario is we are considering a homogeneous isotropic medium free of all sources. Right. What we mean by this is basically rho is 0 and J is 0. Right. So, I do not have any free charges or free currents, conduction currents anywhere in the medium, right, that can create their own electric and magnetic fields. Right. So, I am just looking at a simple dielectric media that is homogeneous isotropic, right, which means I only have scalars epsilon and mu that is being defined, and I would like to see what the Maxwell's equations tell us for this particular scenario, right. Can we come up with one simple solution to the Maxwell's equations in this very simplified scenario? This is what we are going to take up for the next few slides. Okay. So, because rho is 0, our Gauss's law readily simplifies to the form that we have for magnetic fields as well, right. So, both del dot E and del dot H is 0. And then the other two equations involving the curl so remember we are now using H instead of B. So we have curl of E is minus mu dou H by dou T, and curl of H is epsilon right. So these are the four Maxwell's equations when we say rho and J are 0. So there's something that I perhaps missed pointing out, which is all these equations that you see in front of you in this simplified scenario are homogeneous, right, which means to say that if I were to pull all the variables and its derivatives to one side of the equation, I do not have any free constants left on the right hand side, right. So there was a concept of this is do not get confused with the homogeneous medium. I am talking about homogeneous differential equations, right. So the moment the sources disappeared, we find that all four of the Maxwell's equations are now homogeneous, right. They were linear equations. We talked about linearity, them not having any powers of the fields or their derivatives, right. Now with source free regions, we also have the Maxwell's equations to be homogeneous, right. This, remember, what does it allow us to do? In the case of voltages and currents, I said that you can separate the functions for space and time, right? So if you remember, when you have linear and homogeneous differential equations, if you had functions for position and time, you can actually separate these variables, right? That is what the equations allow you to do. We'll do the same thing here as well, right? But here, rather than having to pretend that we don't know what the answer is, we are going to say that we know, right? We know from our analysis of voltages and currents what is the kind of solutions we are going to expect, right? So I want you to also parallelly recall the equations that we got from the frequency domain analysis of transmission lines, right? So what were the equations for voltage and current? We had dou V by dou x. This was the first of the telegraph's equations. Right? I believe there was a minus sign there. Then you have dou I by dou x is minus C dou V by dou t. Okay. The reason to write this down is I want you to see the parallel between the curl equations and the telegraph's equations, right? They look awfully similar. I have the spatial derivatives on the left hand side being equated to the time derivatives on the right hand side through simple scalar factors, right? In the case of voltages and currents on transmission lines, we had the inductance and capacitances per unit length, and here we have the permeability and permittivity of the medium. Okay, so remember what was the trick we did? Since V and I were coupled to each other in this coupled differential equation, we took the derivative of the first equation with respect to x, and then we used the information from the second equation into that to actually get the wave equation for voltage and current, right? We are going to do the same in the parlance of vector fields. We'll have to take the curl again, right? So we do curl of curl E is minus mu dou by dou t of curl of H. Okay, you shouldn't be surprised that I am doing this. I can absorb the curl into the derivative because derivative and curls are linear operators, right? So I can exchange the order in which I do them or execute them. And now I have the expression for curl H from the other Maxwell equation, and so I can substitute that on the right hand side to minus mu epsilon dou squared E by dou t squared, right? I am replacing curl of H with epsilon dou E by dou t. So the right hand side becomes minus mu epsilon dou squared E by dou t squared, right? And on the left hand side there is a relationship. I'll allow you students to sort of do this at leisure, right? So this curl of curl E can be simplified as the gradient of the divergence of E minus del squared of E, right? So this is a vector identity that I am not going to prove here. There are several textbooks where you can look at this this identity, and you should also be capable at this point to prove this identity yourself, right? Just derive the left hand side and the right hand side and show that they are the same. But then in this source free media, we know that del dot E is 0. So the first term is identically 0, and so we get a wave equation for the vector field, right? In this case, I believe we had dou squared v by dou x squared LC dou L squared. Right. So remember the voltages and currents, we had to deal with only single dimension. Here now we have a vector field, right, which has three individual scalar functions, scalar fields, and we have a very compact way of writing the wave equation in 3 dimensions using this notation, which is the Laplacian acting on the vector field E is equal to mu times epsilon of dou squared E by dou t squared, right. So remember, while talking about Laplacian and introducing that operator, I only showed you what the Laplacian when operated with a scalar field look like, right. So you may be wondering what the Laplacian acting on a vector field is. It's just a compact way of writing, right. So remember that this Laplacian would act on each component of the vector field, which are all scalar fields, right. So we'll just write that down. But before leaving the slide, I'll also say that we could have done this for the magnetic field as well, right. So remember, if you were to take the curl of the curl H equation, right, equation 4, let's say. So if I took the curl of equation 4 and then substituted curl of E from equation 3, I would have gotten the wave equation for magnetic fields, and that will also have a same form. Right. So both the electric and magnetic fields obey the wave equation, right. So what are these called? This is a very, very popular wave partial differential equation, has been studied very well, and the solution forms are known in many, many scenarios, right. So just introducing what the Laplacian on an electric field on a vector field looks like, right. So remember, the Laplacian is del dot del right. So now this operates on the vector field E. Since the unit vectors are not differentiable, it only acts on the scalar fields Ex, Ey and Ez, right. So I can write this del squared E So this entire thing would be the x component, right, of the new vector field. So the del square, when operating on a vector field, the output is also a vector field, right. And then I have the Ey component, and finally the z component. right? So the Laplacian on a vector field is essentially this expanded form, right? You can now see why people like using the nabla operator, right, or the del operator. Instead of having to write this out every single time, it's a very compact form of writing the same thing, right? So remember that when I equate this to mu times epsilon dou squared E by dou t squared, I essentially get three independent equations, right? So remember, every time you see a vector field being equated to another vector field, that essentially is giving you three individual conditions, right? So each of the Ex and Ey and Ez components I can equate, right? So this would simply be mu epsilon dou squared Ex by dou t squared. Okay. So what have we done so far? We have essentially looked at a source-free region, a simplified scenario where rho and j are 0, and we are looking at a homogeneous and isotropic media, which means that mu and epsilon are scalars, right? So it's not necessarily free space. We are allowing for there being a homogeneous medium filling the three-dimensional space, and we are asking for some simple solution of this set of Maxwell's equations in this particular scenario. And we notice that we can simplify just like we did in the case of voltages and currents in transmission lines. We are able to get wave equations for the vector fields E and H, right, that have a very similar form, but nevertheless they are involving all three spatial dimensions, so there is a certain complexity associated with that, right? So now we have to start simplifying further. Okay, so let's start simplifying. So remember that linear homogeneous equations, I can separate the time dependent part and the spatial dependent part, so we don't have to quite keep the space and time together all the time, right? So we are going to look at what we call time harmonic fields, right? So just like saying that in the case of voltages and currents on the transmission line, we took a specific frequency of operation, right? So we derived everything as a function of the frequency of operation, right? Similar to the Fourier analysis that you normally do, right? So we are going to say that the vector field, which can be a function of Ex, Y, Z and time, is essentially a vector field multiplied by e to the j omega t, right? So the same phasor notation that we used for voltages, we'll use the same for here. Remember, the actual electric field is just the real part, right? So when we take this e to the j omega t format, remember that dou by dou t gets replaced with j omega, and when I take a second derivative, it's j omega the whole squared, which is minus omega squared. So I have to replace the second derivative with minus omega square and the first derivative with j omega. So we have del squared E is equal to mu epsilon dou squared E by dou t squared. Remember, these are still vectors, right? So for each component you can write this equation, and dou square by dou t square can be replaced with minus omega squared. So we have taken derivatives and replaced them with numbers, right? Algebraic numbers. So essentially we are doing a Fourier analysis both in time and space. Okay. Let's not forget that we also have an accompanying equation all the time. This was true even for the voltages and currents, right? Even though I only showed you perhaps the wave equation for voltage, there's also a wave equation for the current, right? So in the case of the voltages, we had dou squared V by dou x squared being minus omega squared LC times V, right? So this was the case of a lossless transmission line. And what did we say this was? So gamma squared, which is the propagation constant, is minus omega squared LC, right, which made gamma purely imaginary, and we call this J times beta. Right. So here also we have the same situation. We can call this the propagation constant gamma squared, which means that we have gamma is equal to omega j omega square root of mu times epsilon. Okay, we are going to call this j times kz. Okay, you will understand this shortly. Alright, so if you remember in the last week's final series of videos, I talked about the a e to the j k dot r being an eigenfunction for both the del dot and the del cross, right? So let us perhaps make use of that, right, and say what the Maxwell's equations are trying to tell us when we can substitute a similar vector field, right, and we'll see what are the constraints that Maxwell's equations provides to such a vector field, right. So we know the eigenfunctions of del dot and del cross, right, is given by right, where a and k were arbitrary but known constants, right. So what I am going to do is I am going to simplify the k vector and say that let the k vector, because this is of my choice, right, it's an arbitrary choice, I am going to say this is kz ez. I am going to orient my direction in terms along the z axis, right. right? And I am going to ask the question, what is the constraint on the vector A due to Maxwell's equations, right, because of this. So, let us see when we allow for such a solution, right, which is of the form A e to the j k dot r into the Maxwell's equations. Let us see what we get out, right. So, this is to say that I am going to assume the solution for E is of this form. So, I have a constant vector instead of A e to the j k dot r, I am having E naught vector, right, just for association, and then E to the, so here I am going to create a sign convention minus j k z e to the j omega t, right. So, remember there can be a plus or minus here, right. So, I am just using a convention of minus j k z z, but you should be aware of why I did this, right, because I have taken a time harmonic field e to the plus j omega t, right, and remember the t minus x by v gave me the wave that is traveling in the positive x direction, right. So, I want opposite signs for t and x. So, anticipating that for a forward traveling wave in the positive z direction, I have chosen that my k vector be along this z direction, and that the e to the minus jkz allows me to have this propagating in the positive z direction, right. Okay, so we will see what are the constraints on kz and E naught vector, right. So, similarly I can say H can also be written, there is a solution right. So, E naught and H naught vectors I do not know, right. That is what I will need to find out using the Maxwell's equations. So, both of these are propagating in plus z. Sorry, positive z direction.